Ricardo. Vamos a isso? Ok. Bom, muito boa tarde a todos e a todas. Bem-vindos à Lição Anual da Finisterra 2020-2022. Um cumprimento especial ao diretor da Finisterra, que está aqui à minha direita, professor Marcelo Fragoso. Cumprimento extensível ao professor Ricardo Garcia, vice-presidente do IGOT, que aqui representa a escola, não é? Nós vamos, enfim, se não se importa, eu acho que vou falar em inglês antes para que a nossa convidada nos entenda. Now, if you agree, I will speak in English for everybody, in particular for our invited speaker for this afternoon. Okay, at the core of the dissemination strategy since 1965, Finisterra, the journal Finisterra, contributes to a major mission of the CAG, the promotion and dissemination of geographical knowledge. Finisterra publish original research work carried out by our researchers, which are organized in 6 research groups, but our journal aspires to more than the dissemination of research results from our researchers, being increasingly attractive to international authors, especially in the Iberian and American region, and be referenced in geographical publishing in Portuguese language. The CAG direction supports numerous dissemination activities organized by our research groups, but this annual lecture promoted by the Finisterra is the CAG reference scientific event, being the only one that the direction of CAG assumes as main organizer. This lecture has proven to be a stunning initiative, which has brought us outstanding researchers and scholars since 2016 with Michael Storper, Janice Monk in 2017, Tim Cresswell in 2018, Iona Data in 2019, Álvaro Domingues, the first and the only Portuguese in 2020, Jacques Levy last year, and this year Julienne Stroeve. To whom, of course, I welcome the CAG, to CAG and to IGOT, and thank her for her availability to share with us some of our scientific concerns. I am sure that this Finisterra annual lecture will continue to be a reference in CAG and IGOT activities, not only this year, but also for sure in the coming years. So thank you very much, and thank you for coming. Thank you for our audience. I am sure that all of us will enjoy the presentation of Julienne. Thank you very much. Marcelo?
Welcome to the 2022 edition of Finisterra's annual lecture. Thank you for your presence. The annual lecture is an event dedicated to the dissemination and promotion of the journal Finisterra. It is an important moment in the year for the journal when we welcome a prominent geographer to speak on current or emerging scientific issues. The lecture projects Finisterra into the wider space of scientific journals in geography and beyond. Finisterra publishes research articles in the field of geography and earth science, following the open access model and without charges to our authors. It is indexed on many platforms, namely at Scopus and as an emerging source at the Clarivate Web of Science core collection. We are proud to have a prestigious editorial committee that is gender balanced and with representatives from all areas within geography. In this edition, we bring physical geography to the annual lecture. Our goal was to invite a physical geographer with great scientific prestige, and at the same time, with the ability to communicate science to a diverse and wide-ranging public, and whose research would focus on a key topic for the scientific community and society. Namely, climate change and its environmental effects. We are delighted that Professor Julienne Stroeve from the University of Manitoba accepted the invitation to be our esteemed guest speaker. Why should we care about the shrinking Arctic sea ice cover? The lecture title is clearly an overarching and hot topic for the Earth system, offering state-of-the-art knowledge and attracting a diverse public of researchers, professors, students, and other interested participants. Professor Julienne Stroeve Research Group has collaborated with IGOT in the past within the scope of the course on cryosphere in a changing planet in the undergraduate degree in geography, with an excellent lecture on sea ice remote sensing. We hope that this event will be an opportunity to strengthen this link, and that the annual lesson will be an inspiring occasion to deepen collaborations and to develop networked research. Having collaborated with Professor Julienne in the past, I have invited my colleague, Professor Gonçalo Vieira, as an expert on cryosphere and polar research, to follow up with an introduction to Professor Julienne's research, opening a window to this session that I am sure will be very interesting and stimulating. Thank you.
Well, good afternoon, everybody. On the behalf of the President of Institutes of Geography and Spatial Planning, I'm here representing the directive staff, let's say. And first of all, I would like to welcome to everybody, and thanks to Marcelo and Finisterra staff, let's say, from the organizing of this kind of event, and especially thanks to Julienne Stroeve to kindly accepted our invitation to be here today doing this session. This kind of sessions are quite important for the IGOT. Once they fulfill three of our major goals, they are important for our students. They can hear about some thematics from other people with other points of view, let's say, and they can improve and increase their knowledge. They are important for our research and teaching staff. Once we can discuss some leading edge science, we can strengthen our networking, or now our international network, let's in this case. And of course, once it is a completely free and open event, it's also important for society in general. They can debate, they can discuss a little bit about the mainstream thematics as this one today. So from the institutional point of view, this is the kind of event that IGOT aims to have a lot, and of course to be present and support them. So I hope you have a fruitful session. Thank you very much, and I will pass the word to Gonçalo, that will present our keynote speaker.
Okay, good afternoon, everybody. It's an enormous pleasure for me to open this session and to present you Professor Julienne Stroeve. I'm really happy to see such a large and diverse audience, ranging from students, also from colleagues, and many faces whom I'm not aware who they are, but it's really good that they are interested in learning more about the cryosphere and being here. So it's a pleasure to present you Julienne. She is currently professor and senior Canada 150 chair at University of Manitoba. It's one of the more privileged positions in Canada today as a researcher. She holds a PhD in geography from the University of Colorado in Boulder from 1996, where she did a thesis on understanding Greenland's climate variability. She has also been working for about 2 decades, and she's still involved in NSIDC in Boulder, Colorado, one of the most important research on the cryosphere institutions globally. And she has been, and she still is, a professor, so she holds different positions on polar observation and modeling at University College in London. While investigating a bit in more detail about her research interests, I found interesting to read what is written in her page at University of Manitoba, where it's mentioned that she's interested in deriving accurate geophysical variables from satellite data, which involves developing novel algorithms and validations through in situ field campaigns. And that once reliable data is available, then we can further investigate seasonal, interannual, and long-term changes and understand their drivers in conjunction with other climate data. So it goes much beyond geophysics into aiming at a global understanding of how the climate system is influenced by the changing cryosphere and especially sea ice. Julienne has conducted fieldwork in Greenland, Canada, the Arctic, and of course in many areas in the United States, always linked with the cryosphere. And she recently was awarded the European Geosciences Union Julia and Johannes Wirtman Medal, which is awarded to individuals in recognition of their outstanding scientific contributions to the study of the cryosphere on Earth or elsewhere in the solar system. And what the jury describes is that she is awarded for her fundamental contributions to improved satellite observations of sea ice, better understanding of causes of sea ice variability and change, and there also her compelling communication to the wider public. So today she has the challenge to speak in a sitting position, which was a surprise for her, but I'm sure anyway that it will be a new practice for you also, a new challenge. Yes, she has given several keynote addresses around the world on Arctic climate issues. She has briefed former Vice President Al Gore, US congressional staff, various international consulates and military staff, and together with UK and US scientists, she has brought Arctic science to business and policy leaders at the World Economic Forum in Davos, Switzerland. Well, having followed Professor Stroeve's work for several years, I was quite lucky to work with her and other colleagues in a science policy retreat we had a few years ago near Madrid. I really keep excellent memories of those meetings, where with her vision and insight on polar climate and the cryosphere, which go much beyond the role of sea ice, as we will see today, she strongly contributed to streamlining a vision for the key issues for polar sciences in Europe. At this time, she was working in the building up of a white paper on European polar science policy. So I finally thank sincerely Julienne Stroeve for accepting Finisterra's invitation for the annual lecture, and as such also for contributing to the consolidation of the critical mass on polar sciences within the Center of Geographical Studies, IGOT, and also widely at the University of Lisbon, where we have also the College on Polar and Extreme Environments. She will present a lecture under the topic, Why Should We Care About the Shrinking Arctic Sea Ice Cover? And I'm sure we will all come out of this session today with very clear understanding what is the importance of sea ice and why is it so relevant for us, which stand so far away from the Arctic, but in an area where what happens in the Arctic doesn't stay only in the Arctic. Okay, thank you very much, Julienne.
Okay, hi everybody. Thank you very much for that introduction. It's really great to be here, and thanks for being flexible since I did have COVID a couple of weeks ago and couldn't make it then. Yeah, so I'm going to talk about sea ice, which somehow I've spent most of my career doing. It's funny because I didn't originally think I was going to be focused anything on sea ice. I originally had wanted to be an astronaut, and so my degrees were in aerospace engineering for my bachelor's and master's. But then I took a climatology class, and the professor that I took it from in the geography department was doing research in the Arctic. And when I saw the photographs of Greenland and the ice formations, I was just blown away, and I just wanted to go there. So I was very fortunate that he had funds for a PhD student, so I was able to transfer to geography from engineering and do my PhD. And excuse me for my voice, because I'm still kind of recovering from COVID, but I'm better. But, you know, when I started out doing my research, I really, I didn't think anything was really going on in the Arctic, but I knew that it was very important that if we started to see changes in global warming, that we'd probably see the signs first in places like the Arctic, and that these would be the regions that would be changing the most, mostly because they're covered typically year-round by snow and ice. And so this is what got my interest in part as well, was just whether or not these regions are changing and what that would do for the rest of the planet. Now, of course, oh yeah, there's it does play. Closer? Is that better? Oh, sorry. Okay. Yeah, so one of the reasons, of course, why the polar regions are so important is because they are covered by snow and ice year-round. And as that snow starts to melt back, it's going to start allowing the land and the ocean surfaces to warm up, because snow is highly reflective and it helps keep our planet cool. And so in this way, the Arctic has sort of acted as our global refrigerator. But if we do warm things up and the land masses start to warm up and the oceans start to warm up, that's going to accelerate any warming effect that we have, for example, from putting more greenhouse gases in the atmosphere. So, everybody probably knows where the Arctic is. It's very different than the Antarctic in that you have an ocean at the pole instead of a continent. But typically the sea ice has covered the entire Arctic Ocean year-round. So normally you would have some melt back in the summer. But if you look at the orange line, you can see where the winter extent. Let me see if I can do this here. I'm so used to standing. Here we go, the mouse. So the orange line is the winter extent. And actually the sea ice in the Arctic Ocean in some way is constrained by the landmass around the ocean, but it can extend as far south as Nova Scotia. In Canada, it also goes very far south in Bonhai Bay, over on the China side. But then typically in the summer, you melt back that sea ice. So you might have about 14 million square kilometers of the ocean surface covered by sea ice at the peak of the winter maximum. And then you'd melt back to about 7 million square kilometers in summer. So of course you have the ice in the Arctic Ocean. You also have Greenland, which is a very large mass of ice as well, that covers about 1.7 square kilometers of ice. You've also got permanent snow, typically that was around year-round, and about 30 million square kilometers of snow. And of course, you also have permafrost that you're quite well aware of here within the department. So, this has been our Arctic, and this has been our picture of the Arctic. But of course, if things start to warm up, that picture is rapidly changing. Now, obviously, nothing can really beat going into the field and getting out there and seeing for ourselves how things are changing. And I've done a lot of expeditions to the Arctic, starting with Greenland for my PhD. But when I work on the sea ice, I've done different things where I've either stayed in local communities and then traveled out on ski-doos onto the sea ice. We've also taken aircraft and landed on sea ice, or we've done a lot of ship-based work. And of course, ship-based work is quite nice because you have a home base all the time and you can go out and do your research and come back to the ship, which is different like when I've been camping out on the sea ice or out on the Greenland ice sheet. And it can be quite cold. But these studies, while they're really useful, and I really enjoy my fieldwork opportunities, we don't get to see the big picture. We can only see certain regions. For small spatial scales, we only get to see certain times of a year. So when we really want to start to monitor things long-term and think about long-term changes, this is where we start relying on satellites. And so because I came from engineering, it was a natural progression for me to start working with satellite data. And so I did my entire PhD working with satellite data, looking at monitoring the large-scale changes of the Greenland ice sheet with satellites, and then switched to sea ice for after I graduated with my PhD. And so I've worked with lots of different satellites. This is just a nice animation from NASA showing a lot of the US satellites that are currently in orbit. And of course, there's a lot more now as well with the European satellite systems and other countries as well. But these satellites are really key because we can see the Arctic year round. And depending on the frequency that you're using for your observation, you can also see it regardless if it's polar night or if there's cloud cover. And so our longest climatic data record that we currently have of looking at how things are changing in the Arctic Ocean comes from the passive microwave satellite data record. And since the late 1970s, there's been a series of satellites launched with the exact same frequencies that have allowed for scientists to create these really robust data records that document how much of the sea ice is on the ocean. And passive microwave is very useful for us because it's often cloudy in the Arctic. You have darkness for half the year, and so you can't see the surface with visible, for example. But the microwave penetrates through the clouds. And so it's allowed us to document how quickly the Arctic sea ice has been changing. And this is just an animation from the summertime, looking at the summer sea ice record from 1979, showing that, oops, that went way too fast, sorry. Showing that, back in the 1980s, we had about 7 million square kilometers of sea ice. I don't know what happened there. I'll just go to this slide. So yeah, I'm just taking a snapshot now of 3 different years. So 1979, which is the start of our data record, 2012, which was the least amount of sea ice we've had yet in the Arctic Ocean, and then where it was this last summer. And the key thing is if you look in the 1970s, even the 1980s and the 1990s, most of the Arctic Ocean was still covered by sea ice. You would have some melt out happening, for example, here in the Bering Sea sector, and maybe some years you'd have less ice over in the Beaufort Sea, the Chukchi Sea, and more ice on the Siberian side, or vice versa. But in 2002, we had our first summer where the ice had just pulled back from both coastlines, which was quite unusual. And every year since then, we've been seeing that happening. 2012 was the least amount we've had yet, which was about half of what we had back in the 1970s and 80s. And then this year we had somewhat of a recovery, but it's still not a full recovery. So we see that sometimes you get a little bit more ice. This year we had this tongue of old thick ice that was stretched up towards the Siberian side. And that's what really helped keep that ice from melting out. But it was still about 40% less ice overall than we had in the 80s. And one way to visualize that is by just taking the total extent time series. So we're just summarizing all the area of the Arctic Ocean that contains sea ice, and we're looking at how that's changing over time. And, through 2012, it really looked like we were on this precipitous decline in the sea ice cover. And if you look at here, this 2012, I mean, it's quite outside anything else we've seen yet. And it was an interesting summer because it wasn't a very warm summer, but you had a huge storm that came into the Arctic Ocean at the beginning of August. And it was a large enough storm that it actually was able to mix up the water, the heat that's below the ocean mix layer, and created large waves that could melt all of the ice that was still hanging on. And that's what caused this huge drop here. But the 2007 minimum was also a very big surprise to the sea ice community because we lost 26% of ice cover compared to the previous year. And we hadn't seen that kind of change before. And that was implying that something was going on in the system, that the ice had become so thin that if you had an unusually warm summer or a stormy summer, you can take away a lot of the ice. The last decade, we've been sort of stabilized. And I would say, we're stabilized, but we're definitely not recovering to what we saw here in the 1980s. We're still seeing a lot lower sea ice. It's just going up and down from year to year, depending on the weather conditions. So I've been really curious about what would be that next hit that we do to the ice cover that would then remove the rest of it. Because we seem to be in this holding pattern, you could say. The other thing that we've been able to do with satellites is also tell you, well, how old is that ice that's in the Arctic Ocean? And we do this by just tracking each individual ice flow as it moves around the Arctic Ocean. If it survives the summer melt year, it gets aged another year, survives another year, it gets aged another year. And so this is what it looked like in 1985, where the areas in red are ice that's at least 5 years or older. The blue areas are ice that just grows over one winter season. And you can see that in the 1980s, most of the Arctic Ocean consisted of this really old ice. And the longer the ice is in the Arctic Ocean, the longer it has to thicken. So we had much thicker ice. And then here we are today, where now most of the Arctic Ocean is covered by first-year ice. You have a little bit of old ice that's still stretching north of Greenland and the Canadian archipelago. You have some 2- and 3-year-old ice and some second-year ice. But this is one of the reasons why, of course, we don't see the sea ice really recovering, regardless of what happens in the weather during the summer, because this ice that grows over winter typically grows about 1.5 to 2 meters thick. And so you have thinner ice now that can easily melt out in the summertime. And what I found quite interesting, if I look at just what's been happening, we have this stabilization at the moment in terms of the total extent at the end of summer. But if I look at the multi-year ice fraction, so this is all ice older than 1 year, you can see that it's been going down. And then here's our last sort of decade, and it's bouncing up and down. But we're still losing that multi-year ice. So we're having an Arctic Ocean that's covered by thinner first-year ice. So you can imagine if you get the perfect storm setup. So say you get a really warm summer and you maybe get a lot of winds that help push the ice advected out of the Arctic Ocean, that you could then see another big decline in the sea ice, just because we have more of the ocean that's covered by thinner ice than we used to have. The other thing, of course, that's been happening in 2007 was the first time, at least in the satellite data record, but probably much longer, that the Northwest Passage opened along the Canadian archipelago. And this is the Amundsen's route. Excuse me. And that opened in 2007. It hasn't always been open since then. But interesting, this summer, even though we didn't have really low sea ice conditions overall, we had the second least amount of sea ice in the Northwest Passage. The least amount was actually in 2011. So, even in this year, the Northwest Passage was open. On the other hand, the Northern Sea Route has been open every year. Oops, sorry, this should be 2008. Sorry for my typo. And it's been open every year since. So, of course, that's really changing what we're thinking about in terms of access and shipping lanes within the Arctic Ocean, because this has been staying open every year. So then one of the questions, and what I've done a lot of my research on, was trying to understand, well, what's causing the sea ice to disappear in the Arctic Ocean? And in 2016, a colleague and myself, Dirk Knotz, we published a paper in Science that really tried to quantify why we see such a strong linear relationship between how much sea ice we have in the Arctic Ocean and how much CO2 we put in the atmosphere. And so we could quantify that for every metric ton of CO2 that we add to the atmosphere, we melt another 3 square meters of sea ice. So say I were to fly from Lisbon to New York, I'd be melting 3 square meters of sea ice. And this has been really, I think, useful for policymakers as well, because it tells us that with another 600 to 700 gigatons of carbon we add to the atmosphere, we're going to start seeing ice-free summers emerge. And so it gives you these real constraints as to what kind of limits you should stay in terms of your CO2 emissions. And you can see, I mean, the linear fit is really holding. We did this study in 2016, but the fit has stayed. And this is because this is really being forced by increases in downwelling long-wave radiation from increases of atmospheric greenhouse gases. That is a primary driver of Arctic sea ice loss. But of course, it's also local feedbacks. And we know that, of course, when you have snow-covered sea ice, it's quite bright. It has a high albedo. This is an example of what the sea ice looks like in April, when it's still covered by snow before you have the melt season starting. And then, of course, this is what it looks like during active melt, when now you've got a lot of melt ponds, you have open water areas between the ice flows, and then these areas can start absorbing the sun's energy, warm up, and then melt more ice. So we also have, besides the anthropogenic warming signal, of course, we have this positive feedback cycle, and this is one of the reasons of polar regions are so important. But we basically have warming in all seasons happening at the moment. And that's going to cause the melt season to start earlier. And if the melt starts earlier, you get open water formation earlier. That in turn is going to enhance the ice albedo feedback that's always existing, but now it's happening earlier. And the earlier you open the water, the longer the ocean has to absorb the sun's energy and warm up, which then melts more sea ice, leads to more open water in September, which then leads to warmer temperatures in autumn. And then that's going to shorten your sea ice growth season because it's going to take longer for the ocean to release all the heat it gained during summer before the ice can form again. You're going to end up with thinner ice. And then we're going to have earlier formation of open water again. So you have this vicious positive feedback cycle that's really making it difficult for the sea ice to recover. Now you do also have a negative feedback. And you have an interesting negative feedback in that the more open water you have in the ocean in September, the more ice formation you're going to get. And so actually the ice production in the Arctic Ocean is quite invigorated at the moment because you have so much more open water. You're going to grow a bunch of new ice once the temperatures get cold enough for ice to form. And so actually ice growth is quite rapid, is quite enhanced. But again, thermodynamically, it can only grow to about 1.5 to 2 meters. So it's not that really thick old ice that protects the Arctic Ocean from losing its sea ice. And just some examples that kind of highlight this, and that this is a trend in melt onset that's over the satellite data record. So these blue areas are earlier melt onset on the order of maybe 10 days per decade. But if you think about it, we have over 40 years of data now. You're looking at maybe 40 days earlier melt onset, especially in the Kara Sea, parts of the Laptev Sea, also in the Bering Sea and the Chukchi Sea. But if we look at the freeze-up trends, that's where we see the biggest changes. And again, this reflects the fact that the Arctic Ocean is now gaining all this heat in the summertime. And so the ocean mixed layers are warming up. And so you see very late ice formation now happening, especially in the Chukchi and the Beaufort Sea, the East Siberian and the Laptev Seas. And this is where we're seeing these really big extensions, of course, in the melt ice-free season as well. So we can also just look at that and say, okay, well, what is our ice-free season and how many days do we now have ice-free in the Arctic Ocean? Now, the yellow areas are regions where you have about 300 days of ice-free already. And this is really where we've been seeing the winter change in the Barents Sea sector. So a lot of the drilling that Norway does for oil is actually pushing this ice edge further north because you have about 300 days of ice-free conditions. But here in the Central Arctic, typically you have maybe a month or so of ice-free conditions. But these are the trends now from 79 to 2020. And of course, the biggest trends are in the Barents Sea sector and the Kara Sea sector, where again, we've been seeing lack of winter ice in general, and also the East Greenland Sea. But we're also seeing it, of course, in this region now where we have such late freeze up. And so we have an extension of the open water period in this time. And how much ice can these processes help melt? I think it's quite interesting. This is some data that was collected off the Beaufort Sea. So here's Alaska and here's Siberia. And this is where the ice edge was, the black line, 1987 to 2001. And you can see for different years, it's migrating further north. And the colors here represent the temperature. So that's the mixed layer temperatures in the ocean. These are all gathered from actual data. Oh, and I don't know what happened there. Something happened there. Anyways, so this change that we're seeing in the ocean mixed layer temperatures, the amount of extra heat is about 2 times 10 to the 8th joules per meter squared. That can melt about 0.8 meters of thickness. So this increase in the ocean heat content, even with the ice that's there, it's melted quite a bit from below. And this is something we really saw in 2007. And this was some data collected from buoys attached to sea ice in the Arctic Ocean. The red star is for the Beaufort Sea, and the dashed star is for the North Pole. And on this side, you have the surface melt, and on this side, you have the bottom melt. And these are for different years. So the blue is 2007, which again was one of our big sea ice loss years. And you can see the surface melt in the Beaufort Sea, it varies a little bit from year to year. And maybe about 50 centimeters of ice is melted from the top. In the North Pole, it's a bit less, of course, because you're further north. But then you see how much is being melted from below. And in 2007, you had more than 2 meters of bottom melt happening to the ice flow. So that heat that's being gained in the ocean even the old ice that was there is now being melted quite a bit from below. So that's thinning as well. And again, it's another reason why we're not recovering our sea ice, because you just have so much thinner ice that melts away in the summer. And, you know, as a result, so the media and even NSIDC, who I've worked with, we focus a lot on the summer. And, you know, 2012 was a big anomaly. We did have 3.3 standard deviations below the long-term average in terms of what happened that summer with the sea ice cover. But, you know, in May 2016, we had a very early melt onset, and that departure from average was even larger at 3.5. And because they had early melt and early retreat of the sea ice, you then also had very big delays in the autumn. So November 2016 was even a larger standard deviation from the long-term average. So it's getting bigger than what we saw in 2012. And then even in 2020, we had a very late freeze up again. So these are all tied to this mixed layer warming up. And so it's not just the summer sea ice loss that we're talking about. These anomalies are really pushing now into the autumn season as well, which extends your open water period and which also could extend your shipping period in the Arctic. So then we come to the question, well, why does all of this matter? And there's so many reasons why this matters. I could spend days talking about it and we don't have that much time. But I mean, obviously there's, of course, local impacts. There's impacts directly within the Arctic in terms of its climate, in terms of local communities, in terms of the ecosystems. There's also, of course, economic benefits to be gained. I mean, obviously, with the lack of sea ice, there's opportunities for shipping through the Arctic Ocean. There's opportunities for resource extraction. So there are those impacts as well. And of course, there's also global impacts versus teleconnections that are operating between the Arctic and the mid-latitudes. So I'm going to touch on a few of these in a moment. Obviously, I can't talk about all of this, but I just wanted to sort of show that, I mean, it's not just like we heard earlier, what happens in the Arctic doesn't just stay in the Arctic. It has global implications. So I'll just quickly talk about some of the regional impacts, of course, of sea ice loss. And the natural one that we have to think about is the Arctic warming. There was a paper that came out this last year that showed that the Arctic is now warming nearly 4 times faster than the rest of the planet. And this is shown in many different data sets. They were looking at several different temperature reconstructions and reanalyses data sets. And, you know, if you look at where the warming is, so this is the temperature trend, and this is a local amplification relative to the mid-latitudes. You really see it centered here, especially in the Kara and the Barents Sea sector. And in this region, actually alone, it's warming 7 times the rest of the planet. So then again, this is where we've been losing the winter sea ice. And this is important to remember when I talk about mid-latitude linkages in a little bit, because this is the region that is really showing the largest warming because we're losing also the winter ice here. And as a consequence of this as well, you know that a warmer atmosphere can hold more water vapor. So we're also seeing changes then in total precipitation going on in the Arctic. And this is from a paper that one of my postdocs did last year that we published in Nature that was just looking at the precipitation in different observations. So looking at the data record, which is based on station data, looking at atmospheric reanalyses, and 2 different climate model simulations, the CMIP-5 and the CMIP-6. And this is just looking at the climatological precipitation. And it was encouraging to see that at least with the climate models, the pattern of where we see the least amount of precipitation, which is generally over northeastern Greenland and also maybe the Canadian archipelago, and the regions where you see the most precipitation, so like in the Atlantic Sea sector, those are captured pretty much with the climate models as well. But this is a precipitation change from 1979 to 2005. The station data record is actually the only one that seems a bit different. And I think this just shows the challenges of trying to actually collect precipitation data with gauges. They definitely suffer from a lot of biases. But the reanalyses in the climate model show sort of a similar increasing trend in total precipitation within the Arctic. But what we're seeing is that actually this increase in precipitation is coming at the cost of reduced snowfall. So that means rainfall is increasing within the Arctic region. And we're working with a project right now to actually look at this, because if we get this transition to rainfall, and especially when you have rainfall happening in wintertime, and if that rain in the snowpack then refreezes, that becomes a huge problem for the large herbivores that need to break through the crusts to graze in wintertime. And we've been working together with people up in Finland, some of the reindeer herders, and looking at the implications of these changes in rain on snow for the large herbivores. This is just a plot of the trend in rain on snow, or just rainfall. This is just rainfall. And of course, the largest signature is really here in the Atlantic Sea sector, where the precipitation is now turning to rain and not so much snow. But it's also across large parts of Siberia as well. So it's not just focused within here, but this is the largest magnitude of rainfall. And of course, the other thing that we've been noticing is that at least within the Arctic region itself, when you have no sea ice and you have more heat transfer between the atmosphere and, the ocean and the atmosphere, that can provide fuel for storms, because you are seeing more water vapor in the atmosphere. And you start getting these more extreme events. And we're actually working on a paper right now with some social scientists just to look at the impact of what happened in Clyde River last year, because they had several consecutive blizzards that just completely shut down the town of Clyde River and Nunavut, Canada. And while we look at the actual observations of the stations and we don't see that it was necessarily the most extreme in terms of precipitation, it was extreme in the number of blizzard days and how many they had, and just the fact that they also had complete failure of a lot of their equipment. So it's not just that we have local impacts on the sea ice itself, it's actually impacting all the local communities. And they actually ran out of food because they couldn't get the resupply vessels in there as well. So it's also because the community is also changing their way of living, and they're relying more on non-subsistence hunting for food supplies. That, of course, also has a big impact when these events happen. But of course, the sea ice and what goes on there infects the entire marine ecosystem, which then impacts the entire human systems that also depend on the sea ice. So it's not just that I'm concerned about what's happening here on top of the ice, but the light that goes through the ice is limited by how much snow is on it and how thick that ice is, but that feeds the entire under ice biology. It feeds the under ice algae growth, it feeds the phytoplankton blooms, which feed all the fish, which feed the seals, which feed the bears, which feed the people. And so the entire ecosystem is dependent on what is going on with the sea ice cover. So one thing I started looking at, and this was from a paper we did a couple of years ago, was just looking at how the snow depth is changing on the sea ice, because snow is a real big limiting factor. It attenuates much of the light. So how is the snow changing on the sea ice? And so this is just looking at it by month from November through April. And what you see is what you would expect, because we have all these big delays in the freezing up of the sea ice. You're not actually accumulating the snow. So you can see that we have increased precipitation, but it's just falling into the ocean. It's not accumulating on the sea ice. And the only region where we're actually seeing an increase in snowfall accumulating is really north of Greenland and the Canadian archipelago, where we already have sea ice. So it's already there. The snow doesn't fall into the water like it does in the periphery of the Arctic Ocean. So we can take that information, and we can take that information together with the ice thickness fields and start estimating, well, how much light comes in under the sea ice. And I'm just showing two different examples. So I'm looking at PAR, which is micromoles per photon per meter squared per second. And this just shows you areas, the red areas have very large amounts of under ice PAR. So you have a lot of light coming in April. And then you have, of course, the central Arctic Ocean, where you have more snow and you don't have as much light coming in yet in April. The differences between the 2 years is really tied to the snow depth, because that is the main factor that governs early transmission of light through the snow that feeds the under ice algae bloom. But then we can start taking our longer term data sets. And for thickness, you don't have the same long term that we have for sea ice concentration. We start mostly in 2010, but we can then start combining that information with our snow and look at when do we think an under ice algae bloom might happen. And we use a threshold that's quite low, and it might not even be low enough, because data collected during the polar winter in the Arctic actually suggests that you can get under ice algae blooms at very, very low light conditions, even moonlight now. But it will depend on the snow cover. So we're actually looking at, these maps now that we can produce, showing when we expect an under ice algae bloom could happen if everything else is good. So you have enough nutrients in the water column to feed the algae production, for example. So the orange areas are happening sometime in May. And then here you get some of the light could start being enough even at the end of February, early March to initiate blooms. And this is really useful for the ocean biologists then to look at how the under ice biology is changing in the sea ice. And of course, that is crucial for the local communities. And there's a lot of communities in the Arctic still that try to survive off of subsistence hunting. And they also need the sea ice for travel. It's part of their cultural identity. So all of these changes that we see in the ice cover are impacting the communities and in not very good ways. And of course, all the species, whether it's the polar bears or the whales or the seals, they all need the ice for their breeding, for their hunting, for their survival. And so at the moment, with the rapid pace that we're seeing in the Arctic, you have a lot more accidents happening on the ice with people falling through the ice because the traditional ways of knowledge of what they expect the ice to do and the storms is no longer holding. The way the ice is moving is taking the species with them that they're relying on. In Churchill, for example, we now have orcas coming into the bay instead of, well, you still have beluga, but the orcas are coming in and they're replacing the beluga. You've got harbor seals moving in, replacing the ring seal. So all of these food supplies are changing. And actually, one of the indigenous communities tried to catch an orca recently, and they tried eating it and they all got sick. So they thought, well, let's try eating an orca because this is what we have now. But it wasn't the right fish for them, or maybe it wasn't processed right. So their whole way of life is changing. And of course, all the coastal communities are threatened as well because sea ice acts as a protective barrier, protecting the coastlines from waves, from storms. So if you take away the sea ice, and then you can actually get increased fetch, increased waves when a storm comes through. And that together with permafrost thaw is causing a lot of coastal erosion. And a lot of these communities are being forced to move. So, you know, I often, when I see articles about sea ice, oftentimes there's also images of icebergs. And of course, icebergs are not the same as sea ice. Icebergs come from land. And so sea ice doesn't directly impact sea level rise, but by warming up the Arctic, and as it is, it does impact on sea level rise. And this is just an animation from the GRACE instrument that NASA has, which is a gravity instrument that's been measuring how the mass of Greenland has been changing since 2002. And of course, we can see that the melt extent has increased over time. So it's going up to higher elevations of Greenland. It's lasting for longer periods of time. Again, you have more open water even around Greenland. So you just have this warm heat that sits around Greenland. And this year we had the melt kind of a peak happened in September, again, because of lack of sea ice. But then also we had a hurricane that tracked up and hit the southern eastern coast of Greenland and caused melt again. So these changes are impacting, of course, all of us because we're all impacted by sea level rise. And a colleague of mine, Jason Box, just published a paper a couple weeks ago that basically documented at the moment we're committed to at least 27 centimeters now, no matter what we do in terms of our greenhouse gas emissions, just sea level rise from Greenland alone. And this is because the changes in the mass balance and where we're getting the accumulation and where we have the melt pretty much locks us into 27 centimeters. Now you can go to Climate Central and you can do animations about different sea level rise projections and what's going to get flooded. And so I just took this out for the Lisbon area, showing the regions that would be flooded under the current sea level rise projections at the end of this century. And so now that we lock in another 30 centimeters for sure from Greenland, these projections are going to be changing. And, you know, I mean, there's a lot of economic impacts as well. I mean, it's a win-lose situation, I think, for communities. Some communities are very much in favor of what's happening because there's economic opportunities in terms of resource extraction. This is the port of Churchill in Manitoba in Hudson Bay. They're, of course, hoping that there'll be more shipping traffic coming through and more resources that they will be transporting. And, you know, there's a lot of undiscovered oil and gas still in the Arctic. It has about 15%, we think, of the known gas and oil reserves. The problem is most of them are actually on the Eurasian side. Most of them is what Russia has. Norway has a small percentage, and Canada and Alaska do as well. But the majority of all of our known oil and gas reserves in the Arctic are on the Eurasian side. So in this region, I think there's a lot of favorability for wanting to keep the ice open in this region and start exploring and getting more of the resources. But, even in Alaska and of course in Canada, there's a lot of active drilling, and I've done consultations before for oil companies to see like, what is the probability of ice being not there in the future in the regions that they want to drill in. And of course, there's opening of the shipping lanes, and that's a big thing as well. That's starting to gain a lot of traction. In 2012, which was again our record low sea ice year, we had 48 vessels that went through the northern sea route here, and they carried about 1.2 million tons of cargo. And that was compared to 34 in 2011 and 4 only in 2010. So you see an increase of vessels that are coming through. Again, in 2013, there was 31 ships that made the transit through the northern sea route, but it was the first time that coal was carried from Canada to Finland, and it was the first bulk carrier that went across the Northwest Passage. So we see this increase in shipping. In 2015, the Chinese vessel Yongshen finished a record-setting round trip from Europe to China. And in 2016 was the first time the Crystal Serenity was a cruise ship, went through the Northwest Passage with passengers. And I just looked this up the other day. In 21, now we had 85 transits. So it's nearly double what we saw back even in 2012. So the amount of shipping traffic that's going through the northern seaboard is increasing dramatically at the moment. So now I just want to touch a little bit on global impacts, because of course what happens in the Arctic doesn't stay there. It does have impacts for the rest of us. And, the biggest impact, of course, again, we know the Arctic is warming so much faster than the rest of the planet. And this is just an example of what it was in 2019 in terms of where you had warmer and colder conditions. And the entire planet is warming, we know that. But with this temperature changing so much faster than the mid-latitudes, you're changing the temperature gradient between the equator and the pole, which drives our large-scale weather patterns, which are basically trying to take the excess heat that you get at the equator and move it northwards to the pole. So we're altering that temperature gradient. Now, where the debate is in the science community is, how is that impacting our weather? How does that impact the jet stream? Because the hypothesis has been that if you change that temperature gradient between the poles and the equator, you slow down the zonal wind speeds. So you slow down the jet stream, basically. And if the jet stream gets slower, it gets wavier. So then whatever weather is happening on either side of these kinks in the jet stream, whether it's a high pressure or a low pressure, they get stuck for longer. So then you get persistence of whatever that weather pattern is that can lead to extremes. So that's a hypothesis that's been going, and there's many articles about this. It's a hotly debated topic because there's also so many things happening in the climate system at the same time. But we do know the zonal wind speeds are slowing down. How it's perturbing the jet stream, I think, is still an open science question. But there's a few links that are getting a bit more concrete. And one is we turn back to the Barents and the Kara Sea sector, where we don't have the winter ice anymore. And when you looked again at that temperature map, you have 7 degrees of warming now compared to everywhere else on the planet in that region alone. Now that is perturbing the troposphere. It's perturbing the Ural sea level pressure, which is a high pressure ridge that sits over the Urals. Now, since you're perturbing that high pressure, it actually can communicate with the stratosphere. And the hypothesis has been that it's actually starting to weaken the polar vortex. And so when we get these extreme weather events like snow in Texas, it's usually because the jet stream has gotten, the polar vortex has gotten more wobbly. It's no longer this really tight, spinning fast winds around the polar vortex. It's actually starting to get bigger and get more wobbly. And then that allows cold air from the Arctic to spill out and go into the lower latitudes. So like the beast from the east, I don't know if that hit Portugal. I was here in England when that happened. Again, that was linked to a breakdown of the polar vortex, which evidence really shows that it's probably quite strongly linked to what's happening in the winter ice cover in that sector of the Arctic. There's also new studies that have come out that are suggesting that the droughts that we're seeing in California, and also the high pressure, the heat waves that we had in Canada last year, could also be a result of sea ice loss. That the sea ice anomalies leads to a perturbation where you have the energy transfer from the polar regions in the Pacific sector goes down towards the equator, and that actually decreases the convection and divergence aloft, which sets up this Rossby wave train that brings high pressure over North America. That was published in 2017, but it seems to be another possible linkage between what goes on in the Arctic and extremes at lower latitudes. And then finally, I mean, there was a new report by the WMO that just came out and said Europe is actually now warming 2 times the rest of the planet. So if we think about the global land masses, Europe is actually warming more than other land masses. And some studies suggest that this couldn't have happened without amplified warming in the Arctic, that this is part of the reason why we're seeing this increased warming and extremes within Europe. And, you know, we had this big Siberian heat wave, and other papers have suggested that that could not have been possible without our human-induced warming. So, I mean, everything is connected. We know that. It's hard to take out each individual extreme event to say, okay, that was caused by the Arctic, but the whole system is connected. And I do think that the Arctic is starting to show its fingerprints on a lot of the extreme events that we're seeing around the world. So I just wanted to end a little bit on just the fact that I think we're quickly running out of time in the Arctic. It's changing so quickly. And to try to understand these implications, we really are needing to do a lot more research. And it was one reason why the Germans froze their ship into the ice for a full year during the Mosaic expedition, which took place between 2019 and 2020. And they invited scientists from around the world to join. They had over 600 scientists. And the whole goal was to try to get a better understanding of all the processes that are operating in the coupled ice ocean atmosphere system and do it over a full annual cycle. And especially at a time where we're not usually in the Arctic, which is in the winter. And this just gives an example of the different legs. So they broke it up into stages. All the boats set sail from Tromsø, Norway. This was leg 1, which went at the end of September, and it found an ice floe that it attached the ship to. And then it drifted over here for leg 2. I came for the leg 2, the winter leg. So I arrived at this ship mid-December. And then we floated again for, well, I left it, I guess, second week of March. And then leg 3 came, and they were only supposed to be there for a few weeks, but then COVID happened. So then they were there for about 5 months. And it just shows you the different drift tacks that were taken. They had to leave the ship and then bring it back for leg 5 to finish the full year. So they couldn't stay with the same ice floe for the entire year, but also that ice floe would have been drifted out of the Arctic before the full year because the drift was so fast that summer that they would have been spit out anyways. But we got close to the pole. This is just an example of, oh, I don't think this will play. No. Oh, well. Let me go back. So this is what it looked like when I was going to the ship in the wintertime. So they always had a spotlight to make sure they avoid the heavily ridged ice. So I spent 3 months in the dark during Mosaic with no sunlight. But for me, it was exciting because it was being able to collect data at a time we're not normally there. And it's also for me exciting because, you know, we have to revisit our algorithms because all of our satellite algorithms are based on a time when we had thick ice, cold snow, lots of snow, and those empirical fits that we've done, a lot of it to data that was collected, are no longer maybe applicable in today's new climate system that we're having in the Arctic. So during Mosaic, we deployed several instruments that are the same as what we have in space right now. So we deployed active and passive microwave instruments. We had visible and thermal infrared instruments. This is what it looked like when I was there in terms of all the instruments we had. And the idea was that they'd look at the same piece of ice, the same piece of snow area, so that we could better understand all the processes that influence the energy that we're retrieving so that we can improve our satellite retrievals. This was an instrument that I brought specifically, had it built brand new for the expedition. It was a dual frequency radar, so it had Ka and Ku band. And it was our first opportunity to collect these dual frequency observations over sea ice because the European Space Agency has now approved the Crystal mission, which will fly these 2 frequencies as an altimeter on their satellite. And so we wanted to collect the data that would basically say whether or not this satellite mission would achieve its science objectives. And I just want to give you guys a sense of what it looked like, not on my leg because it was dark, but this is what it looked like on leg 5. And the way Mosaic was structured is you had different camps set up around the ice floe. This was a remote sensing city where we had the remote sensing instruments. This is where the MET towers are. So all the atmospheric measurements were kept over here. This is where the underwater robotic vehicle was operating. This was the ROV area. Some of these are like snow areas or biogeochemistry areas where people would collect other kinds of data. We had Ocean City as well. There's a CTD over here. So all the idea was that we would all be collecting data for each other throughout the full year, and we'd be sharing all this data with each other so that we can actually just improve our understanding of what's going on in the Arctic Ocean. So I just want to mention one thing, since I mentioned rain on snow. We actually had the opportunity to collect data during Mosaic where we had new snow on the sea ice and then it rained. And then after it rained, it refroze. And so we had these ice layers in the snow. And I've been very curious because I know that we're seeing these increased trends in rain happening in the middle of winter. How does that impact the energy that we're retrieving from satellite, and how would that impact our algorithms? So this is just an example of when we had the instruments out there during the rain event. And we also had a course snow cores, so we could look at what happened in the snowpack. We had the density structure changes, which is something you never get. So if we're seeing a rain on snow event detected, we're not out there in the field looking at what it did to the snowpack. So I'm just going to quickly run through this. It's maybe a bit complicated, but just a couple examples of what we did. So we had a surface-based radiometer similar to the satellite that I was showing all the results of the sea ice changes over time with. And this is two frequencies, 19 and 89 gigahertz, and two different polarizations. So we had vertical in the dotted and solid is the horizontal polarization. These channels go into our sea ice algorithms. And this is the first rain event, this is the second rain event, and this is just when temperature stayed above zero. So we had liquid water that percolated in the snow. During the liquid water, you get a big jump in the brightness temperatures, and that because now the emissivity approaches that of water, so that's one. And then we have the second event, and we start seeing this refreezing eventually, and the temperatures drop again. The interesting thing for me was that this difference between the vertical and the horizontal got bigger because they were responding to the ice layers in the snow. And that would have caused an underestimation in how much sea ice was there with the passive microwave algorithms. We also had our active radar, so the KUKA radar. This is Ka band and Ku band. Now I'm looking at range. So this is actually the depth, where the power is being returned from within the surface and the snow below the radar. And again, it's a very complicated plot, and I don't expect to really go into details of this, just to say that when the rain event happened, and we did have a power outage, you lost all the energy that's coming from within the snowpack. So you're not getting any return from down there. You're getting it from the surface area. But afterwards, we still see a change in the overall energy that's coming back, which is interesting in some sense, but we were really interested in the shape of the waveforms and how those are changing during the rain on snow event, because the waveform shape goes into our thickness retrievals from altimeters like Cryosat-2 or Altica. So this was another thing we did. If you can read more about it in a paper if you're interested in radar altimetry and the impacts of snow and rain and ice layers. So I'm just going to quickly conclude with what it's going to look like in the future. You know, if I think about global warming and we're trying to limit it to 1.5 degrees, and we have maybe 10 years for that, and maybe half of that, depending on what's happening with the permafrost. You look at this for global warming, but this is the Arctic warming. And I'm just looking at two different emission scenarios, which are pretty much the same at 1.5 degrees anyways. But you're looking at winter warming of 5 degrees, or actually in autumn, you're looking at 8 degrees of warming in the Arctic. So it's not 1.5 degrees in the Arctic. It's more than twice that. It's almost 3 times that warming. In the summertime, it doesn't change too much because the heat goes into melting of the snow and ice, but you get this huge signature in the autumn. If we go to 2 degrees, the warming gets even larger. Now you're getting above 9 degrees of warming in the Arctic under these 2 degree scenarios. And you're going to have a very different climate up in the Arctic. It's going to change the Arctic beyond contemporary recognition. And we know already that sea ice disappears in summer at 1.7 degrees. So we've done these simulations looking at the CMIP6 models, but also with the observations. At 1.7 degrees, we already start losing the summer sea ice. If you go to 2 degrees, you're going to have ice free for a couple of months of the year, and it's just going to get longer and longer. So this is the future that we're facing at the moment. So we looked at just changes in ice free conditions and looking out into the future. This column here is for days of 270 days of ice free and what decade that will happen. I mean, that's going to happen more at the end of the century. But if you're looking at days of like 180 degrees, 180 days of ice free, you're starting to see this is going to happen already at some of these decades. This is the business as usual. Sorry, this is the most conservative, where you can keep the ice until the end of the century. But here already, you're starting to see, you know, by 2060, large parts of the Arctic will already be ice-free for 6 months out of the year. So this is a big transformation. This is just the temperature at which it happens, which we don't have to go into necessarily. And then finally, I'm just looking at the precipitation changes. So these are done by two of my different postdocs at the University of Manitoba, but we're looking at the winter rain and this the autumn, and this is snow, and this is rain. This is snow, sorry, and this is rain. And this is all CMIP6. So you see that there's a decline in snow, especially in the Atlantic sector and also in the Barents Sea sector. And you do get an increase in snow in winter, but you're also seeing an increase in rain that's going further up north. But then in the autumn, you see that the snow cover is pretty much going away, and it's all going to be falling as rain. And this column is just the difference between CMIP6 and CMIP5. And the thing that we were noticing is, at least in the CMIP6 climate models, this transition happens a couple decades earlier than it did in CMIP5. So I'm just going to leave it with this. I do get involved with Arctic Base Camp, which is an event that we do at the World Economic Forum every year. And we have this new Arctic Risk Dashboard. And the Arctic Risk Dashboard allows you to go and get up-to-date information about various parts of what's going on in the Arctic itself. You also have an opportunity to create your own name badge with different climate things. I took Sayonara Sea Ice, but there's many different things that will come up if you type your name, and you can get you know, something about flooding or more monsoons or things like that. But it's really trying to connect what's going on in the Arctic to global risks everywhere. And I find it it seems to be quite popular now, because I think business leaders and policymakers are trying to figure out, you know, what can we do and what are the global risks associated with what happens in the Arctic. Okay, thank you. That's 50 minutes.
Let me open the floor for questions. Hello.
Okay.
Yeah. Okay, thank you very much, Julienne, for this excellent talk. It is amazing how encompassing are changes in the Arctic sea ice, and how it really cross-cuts along different fields, which are really relevant for us geographers. So it touches human geography, physical geography, GIS, mapping. So I would open the floor for questions from the public. So maybe I will break the ice with a question. Yeah, so two topics. One of the things is you mentioned it briefly. Well, not briefly, but in fact, there is this concept that derives from what is happening in the Arctic, and also associated to essentially biological changes that come afterwards, the changes in the ice, which is this Atlantification of the Arctic, or Atlantization of the Arctic. Could you tell us a bit more about this? Because I see that there are big changes in the sea ice that are affecting also the movement north of different species. And this is something that also affects us Portuguese. We like fish very much. We are big eaters of cod. And what is happening in the Arctic really can affect us all, because we are fishing also in the Arctic.
Yeah, well, that is a good point, and I didn't touch on Atlantification. It was hard to figure out how much to put in, because I could talk for a long time. But yes, Atlantification is basically the fact that the Atlantic, we had these pulses of warm water coming up through the Atlantic, and that is largely driven by not necessarily what goes on in the Arctic. It has a lot to do with ocean circulation patterns that do vary, sometimes on like 60-year timescales. But the problem is that because you've been melting the sea ice, what normally happens in the Arctic Ocean is you melt the sea ice, and then you have this cold freshwater layer that sits on top of warmer water at depth. And because you have a very strong halocline, that water does not mix. But what's been happening, and why we're calling it now Atlantification, is that warm Atlantic water is now starting to reach up to the surface layers, and it's starting to reach up underneath the sea ice, especially in the Eurasian basin. And one of the reasons why that this is happening, well, when you have a lack of sea ice, you're not melting sea ice now in the Barents Sea sector, for one. So you're eroding the halocline in that region. So that's allowing that Atlantic warm water to go closer to the surface in that region. And so we see that happening. And of course, you can imagine that the fish species are then also going to be moving along with that warm water and the changes in the ocean patterns that are happening within the Barents Sea sector. I know off the coast of Greenland a few years ago, they caught a tuna, and they didn't know, this was on the east coast of Greenland, they didn't know what to do with it because they have no right to fish a tuna. So they couldn't sell it, for example, because they don't have a license for that. So they had to try to distribute it to the communities, but it's a, tuna is a big fish. And they had a lot of trouble trying to figure out what to do with that tuna. But you do see this happening. And on the Pacific side, you're also seeing these changes as well. It's the Pacific side, you definitely get a lot of warm water that comes in through the Bering Sea sector. And sometimes that water does also make it, I think, to the underside of the sea ice. But it really influences the migration patterns of the whales, especially in that region. And of course, all the walruses as well that are, wanting to eat all those shallow shores there in the Chukchi Sea. So, I mean, all of this has implications for the entire ecosystem there.
And also with the increasing exposure of the coast of permafrost, increasing erosion, all this mercury that is trapped on permafrost is being released to the nearshore zone and will be integrated in the trophic chain. So normally we think about the problems it impacts on local harvesters, on people who fish and live on those fish communities, but in fact it also will affect everybody who will feed on those fish. So potentially there can be issues also related to other populations, non-local, non-native populations associated with that.
Yeah, I think it's going to be really interesting to start seeing the data from the eco team coming out of Mosaic, because they did a lot of catching of fish. They did a lot of sampling of just the water column and what's in the water column. And I think it'll be really interesting to see the results from the biogeochemistry and the eco teams, because, we don't know enough about what's happening in the Central Arctic Ocean. The one thing we did find that we already had a paper come out on was that, normally you don't think you can have platelet ice formation under Arctic sea ice because you don't have that fresh water necessarily down there like you do in the Antarctic, where you have these floating ice shelves that release all this fresh water. So, but we did see platelet ice formation in winter underneath the ice in the Arctic as well, which was quite interesting to see. But it was, so when I was on Mosaic and we were near the pole, I was sitting in the ROV tent because twice a week I would help out with the underwater robotic vehicle that was doing the net trawls and doing the different mapping the underside of the ice with sonar and things like that. And I was waiting for the ROV to come up out of the hole, and a seal popped its head. And we never really saw much fish in the Central Arctic Ocean. We never, this was in the winter, and we didn't really catch any fish. But we did see some juvenile cod, and then we found the seal later with the ROV hanging out underneath the pressure ridge, which was a bit surprising because we were quite close to the pole. We also had a fox come by in the middle of winter, which also was a bit surprising because the fox would need to eat the leftovers from the polar bears. So we did get a bear come by as well in the middle of the night. But I saw the fox, then we saw the seal, then we saw the bear. So we did it all in the wrong order.
Okay. The other question I have is, it is related essentially to our students and to the potential that you see, if you see any potential on the way that Portuguese students, which can be based also in Portugal, but they can move, of course. But since we are investing so much in GIS, there is so much technology available to do remote sensing work. In which way do you think that students based in Portugal could contribute to research independently of doing field work or not? So can you tell us a bit about this?
Well, I mean, obviously I work with satellite data, so you don't need to go to the field to work with satellite data. And there's so many more satellite systems coming up that there's amazing new data, especially I think the work that Copernicus is doing and the European Space Agency with their new satellite missions is providing so many new opportunities, and more so than the United States now, because the United States is, I mean, the sea ice data record that I was showing was all based on data collected by US satellites, but that satellite program is not being renewed. So we will have a data gap. But now the European Space Agency is looking to fill that with their new satellite missions. And I think so for being in the EU, I think there's a lot of opportunities within EU remote sensing work. And there's also exciting opportunities too in the fact that, you know, there's a lot of investment now by the EU to do these digital twin Earths. So I work with climate models, but I work with lower resolution climate models. But the new approaches are going to be to run things at very high resolution so that we can do simulations where we can even incorporate human decision-making into the outcomes of what the model simulations show. And this will require observations for validation too. So you need to work with the satellite data to validate these climate models and make sure that they're actually representing the processes that we understand. So I mean, with satellite remote sensing, of course, you don't have to go to the field to do work with satellite data, that's for sure. And yeah, there's a lot of new missions. Like I know the new Earth Explorer mission from Harmony. I mean, if you're interested in solid Earth deformation, if you're interested in ice sheet deformation, if you're interested in ocean atmosphere interactions, the new Harmony mission is basically designed to address those topics at very high spatial resolution. So that's just got approved by the EU. And so that will move forward and be launched probably in 2029.
Excellent. So there is a lot of data coming up, and so human power and brains are needed. So I think there are several opportunities, and sometimes even Portugal's, as you may know, there is some funding that's available always for the member countries to be used on research. And I remember a few years ago, Portugal was kind of striving to fund some projects. So there was money available from ESA, specifically for Portuguese research activities. Okay. Yeah.
Well, yeah, and on that, I mean, I'll mention, of course, ESA is going to be doing a lot of new tenders to design studies with their new satellites. So they have Crystal, which is going forward, which is a dual frequency altimeter. They've got Simmer, which will be the replacement of like the US SSMI type satellite. And they've got the Harmony mission for sure. These are approved missions that are coming, and they will have tenders, of course, to do science with that data. And it doesn't have to be cryosphere. It can be any, you know, physical field of observation.
So since I broke the ice, are there further questions? Please.
More water will be available in our situation. Can this explain sometimes the unequal distribution of rainfall, for example, what happens in Southern Europe with recently with a spring drop of 2021 drop?
I think I might have missed the first part of the question.
Can you repeat?
Yeah. Okay. Yeah, I mean, I think, you know, these type of attribution studies are always going to be challenging because you have many things happening in the climate system at the same time, right? So saying that changes in, for example, an extreme event like droughts over Portugal that is linked to Arctic sea ice is it's challenging, because what about the El Nino phase, or what about other things that are happening in other parts of the climate system? But I think where the robustness is really starting to come is perturbations. If the perturbations are large enough that you get tropospheric, stratospheric interaction, for example, that affect the polar vortex, that is one thing that seems to be quite robust now. And I think the other ones are still a little weaker, because the problem is different climate model simulations, by taking away the sea ice and looking at what the atmospheric response will be, they vary between models. They vary between experimental design. And I think that's where the challenge has been. I would say that, I mean, there are more and more studies that are starting to find more robust linkages, but at the same time, you could probably find quite a few that would challenge that. So I think the jury is still out. I know that that's not exactly what like media wants to hear when they talk to us about an extreme event, but I think we have to be cautious about exactly how much we can attribute one thing to one part of the climate system. But I would say everything's connected. And of course, if you start seeing, if you can identify the mechanism whereby a high pressure system, for example, over Portugal comes and sits there and creates this extreme event. And if that's linked to a Rossby wave train that's being driven by Arctic anomalies, then yes, I would say it would be. But I don't know, because I haven't looked at that myself.
More questions? Okay, so if there are no more questions, I think we'll move on. I would like just to thank again to Julienne Stroeve for the fantastic presentation. I'm sure we are much more aware of how the Arctic is changing about the sea ice changes. Thank you very much, Julienne.
Professor Julienne, just to again thank you, your kind acceptance of our invitation for this lecture. It was really an outstanding lecture, very, very interesting. And symbolically, to end this lecture, I would like to offer you just a symbolic gift, a souvenir from this occasion, okay? You may see.
Thank you.
Thank you, Julienne.
Thank you.
Obrigado a todos. Dizer que vamos prosseguir a nossa sessão com a atribuição de prémios já de seguida. Portanto, convido a todos para ficarem, porque vamos passar à atribuição do Prémio Melhor Artigo do Ano da Finisterra de 2021. Muito obrigado a todos que vieram assistir à Annual Lecture. Muito obrigado. E espero que fiquem. Boa tarde outra vez. Peço então a vossa atenção. Dizer que estou muito satisfeito pela vossa presença nesta atribuição do Prémio Artigo do Ano 2021 da Finisterra. Esta é uma iniciativa que consideramos muito importante para reconhecer e divulgar a investigação de excelência que se publica na Finisterra, contribuindo para a disseminação de nova investigação no domínio da geografia. Eu queria publicamente manifestar, em nome da Finisterra, o meu apreço e agradecimento pelo trabalho dedicado do júri deste prémio, presidido pelo professor Nuno Costa, no estudo dos artigos científicos publicados em 2021 na Finisterra. Foram publicados ao todo 35 artigos, no trabalho editorial da equipa antecessora, liderada pela professora Margarida Queiroz, que aproveito também para saudar. Ao júri do prémio, muito obrigado pelo trabalho de leitura, seleção e análise cuidada dos documentos publicados, e passo a palavra ao professor Nuno Costa.
Boa tarde a todos e a todas. Agradeço as amáveis palavras do meu colega e amigo e diretor da Finisterra, o professor Marcelo Fragoso, e, no fundo, cabe-me a mim, como presidente do júri do Prémio Finisterra 2021, endereçar algumas palavras acerca da atribuição deste prémio. Antes de mais, quero agradecer a todos e a todas as autoras e autores que têm escolhido a Finisterra para a publicação dos resultados da sua investigação e, naturalmente, a qualidade dos trabalhos apresentados permitem que a nossa revista seja uma importante referência da geografia em Portugal. Portanto, a todos elas e a todos eles, este meu sentido agradecimento. Depois, agradecer à equipa da Finisterra, liderada pelos meus colegas, professora Margarida Queiroz e agora o professor Marcelo Fragoso, pelo trabalho desenvolvido e que tem permitido publicar 3 números por ano e com a qualidade que é reconhecido ou que é reconhecida por todos. E, naturalmente, aos meus colegas de júri, o professor João Cabral, o professor Carlos Teixeira, que está do outro lado do Atlântico, a professora Maria Helena Esteves, o professor Sérgio Oliveira, a professora Raquel Melo e a professora Ana Louro, pelo árduo trabalho que desenvolveram ao longo do processo de seleção e de escolha do artigo da Finisterra 2021. O trabalho foi difícil, de facto, pela grande qualidade dos artigos, mas que foi superado pela bondade, pela boa vontade e pelo empenhamento de todos. E por isso mesmo, o meu profundo agradecimento a eles. E por último, ou explicar-vos um pouco como é que se desenrolou o processo de escolha do artigo do ano. No fundo, tivemos 3 fases, tal e qual como em processos anteriores, em que foi solicitada a cada elemento do júri a escolha de 4 artigos que, na sua opinião, se afirmavam com qualidade para serem distinguidos. Desta fase resultaram a identificação de 14 artigos. Face àquilo que o professor Marcelo disse, vê-se bem a qualidade que estes artigos tiveram, porque na verdade tivemos aqui, logo de imediato, 14 artigos escolhidos. No entanto, tivemos que reduzir este conjunto para 7, sendo incluídos todos os artigos que tivessem pelo menos 2 ou mais nomeações por parte do júri. A fase seguinte foi, tendo por base esses 7 artigos, foi solicitado a todos os elementos do júri que escolhessem e os ordenassem por uma pontuação de 1 a 3, e após isso, chegámos à fase final, foi reunido o júri para a análise das classificações e a determinação do vencedor. Posto isto, foi um processo relativamente longo, mas muito interessante e foi possível de realizar, apesar de nós estarmos em momentos diferentes, muito afastados uns dos outros. O nosso colega no Canadá, nós aqui em Portugal e depois ele nos Estados Unidos e o resto dos colegas aqui em Portugal e no Canadá, foi possível realizar esta tarefa. E no fundo, o júri decidiu escolher um artigo como vencedor e atribuir uma menção honrosa a um outro artigo que achamos naturalmente ser merecedor desta distinção. E esses artigos vão ser anunciados de seguida pela minha colega professora Margarida Queiroz, a qual passo já a palavra.
Obrigada, Nuno. Eu vou ser muito rápida. Queria, em primeiro lugar, agradecer o convite para estar aqui hoje para entregar estes prémios. É com enorme satisfação que vejo que o trabalho iniciado há um tempo atrás tem continuidade. É para mim muito relevante, e para nós todos enquanto comunidade da geografia, é importante pensar e ver que a revista continua a ser procurada por colegas que têm já uma carreira consagrada e que se juntam a colegas mais jovens, e que a nossa revista continua precisamente a atrair pessoas em carreira consolidada e ao mesmo tempo promovendo o trabalho de jovens investigadores e investigadoras. E é também importante perceber que a publicação de ciência em língua portuguesa continua viva e, portanto, a Finisterra está aqui também para dar apoio a quem quer publicar na nossa língua, comunicar boa ciência, mas também noutras línguas, como vocês sabem. Ora bem, eu passo a apresentar o artigo vencedor, porque também não dá para continuar o suspense. O melhor artigo de 2021 e é atribuído pelo júri, é dado ao texto intitulado Perfis Territoriais de Criminalidade em Portugal 2009-2019. É um artigo sobre as disparidades espaciais associadas à criminalidade e é da autoria de investigadores da Universidade do Porto, jovens e mais consagrados, como é o caso de Miguel Saraiva, Amante, Teresa Marques, Márcio Ferreira e Catarina Maia. Todos da Universidade do Porto. É uma honra, um prazer enorme atribuir este prémio. Não sei se estão cá todos, se só está cá uma pessoa que representa, que é o Miguel. Miguel, muitos parabéns, continua a instituição. Damos a palavra ao Miguel ou esperamos para Miguel sentar aqui para falar? Queres dizer algumas palavras? Sim, claro que sim.
Boa tarde a todos e obviamente agradecer muito o prémio que é atribuído, portanto, e tomo as palavras agora ditas, portanto é importante continuarmos a ter este tipo de plataformas para publicar em Portugal e, se quisermos, em português. E foi uma decisão da equipa fazermos isso e estamos muito orgulhosos que tenha chegado a este ponto, obviamente. Portanto, deixar o reconhecimento ao júri que selecionou e, obviamente, aos coautores, nos quais eu estou aqui em representação, portanto, a professora Teresa Marques e os investigadores Amante, o Márcio Ferreira e a Catarina Maia. Pronto, muito obrigado a todos, não me vou alongar mais. Obrigado.
O Miguel já tem uma carreira também já de nome na área do planeamento e ordenamento do território, inclusivamente na revisão do PNPOT, e portanto também já é uma rising star e enquanto pessoa convidada para estar aqui a apresentar este prémio, a revista agradece a continuação do investimento na comunicação da ciência e que vocês nos continuem a trazer boa ciência, que nos leiam, porque a revista precisa de ser lida e ser citada. O trabalho que fazemos é bom, merece um lugar de destaque no panorama editorial internacional. E, portanto, muito obrigada e muitos parabéns e continuação de um bom trabalho e cumprimentos à equipa lá no Porto. Pensava que tinha vindo mais alguém, mas não. Ora bem, passando agora a anunciar a menção honrosa, que é atribuída pelo júri ao artigo intitulado Avaliação da exposição das comunidades locais a incêndios rurais. Ora bem, este artigo, assim muito genericamente, dá indicações para a hierarquização das ações de proteção e emergência adaptadas aos contextos locais e é da autoria da Ana Gonçalves, da Sandra Oliveira, da Ana Sá, Acli Benali, do José Luís Zezer, José Miguel Pereira. Ora bem, aqui temos um texto que é resultado de uma colaboração entre o ISA e o IGOT, creio eu, se não estou em erro, e portanto a Universidade de Lisboa aqui também está de parabéns, tal como a Universidade do Porto, e também temos aqui professores, investigadores de maior renome e portanto com responsabilidades digamos, em trazer a gente nova. E eu gostava de saber quem está cá, que eu acho que é a Ana Gonçalves, não é? Ana. Ana, muito parabéns. Um bom trabalho e muito orgulho também da nossa casa, esta jovem que aqui está hoje. Ana, queres sentar e dizer algo? E abre mais uma cadeira, a outra cadeira está ali.
Muito boa tarde a todos, muito obrigada por também estarem aqui presentes. Quero agradecer desde já a menção honrosa que me foi atribuída, não estava à espera, muito obrigada. Quero também agradecer a quem coordenou este projeto por me ter deixado participar, por ter a oportunidade de participar ainda no meu mestrado, foi uma grande oportunidade e com um grande aprendizado que também tive. E queria agradecer também a todos os meus colegas e também autores deste artigo, a professora Sandra Oliveira, o professor José Luís Zezer, que estão aqui presentes, e também aos meus colegas do ISA, que foi muito bom aqui ter um trabalho com outra instituição, também ao Acli Banal e à Ana Sá e ao professor José Miguel. Então, obrigada. Obrigada.
Tenho só pedir que tirem umas fotos para também ser
Tirar uma foto.
Fiquem alguns estudantes.
Boa tarde. Aos que ainda estão presentes, também volto a pedir só uma atenção para o último momento. O último momento ligado com este evento da Finisterra prende-se com o lançamento de uma nova edição do concurso Livros que Contam e em nome da Finisterra também queria expressar o nosso interesse e gosto em manter e renovar esta parceria com a Biblioteca do IGOT, esta iniciativa Concurso Livros que Contam. E foi com muita satisfação que, na sequência da edição anterior, já publicámos 2 recensões da autoria de jovens investigadores do IGOT em 2022, no número 120 da Finisterra. Esperamos que a leitura de novos livros disponíveis na biblioteca continue a ser uma inspiração e um estímulo para a reflexão crítica e para a elaboração de textos analíticos interessantes, e a Finisterra está aberta, receptiva, a receber esses trabalhos, desejando que os jovens investigadores ganhem também uma maior identificação com a Finisterra, como revista de acesso aberto, de referência, para publicar, agora e no futuro, novos conhecimentos no domínio da geografia. Passo a palavra ao meu colega, Sr. Jorge Malheiro.
Bem, boa tarde a todas e a todos, muito rapidamente, porque isto é a parte mais de detalhe. A biblioteca também está muito satisfeita por manter esta parceria com a Finisterra. A ideia da biblioteca é estimular a leitura e a reflexão em torno do que se lê, e é esse o objetivo deste concurso Obras que Contam. E o que queremos é aproveitar o trabalho. Já não estão muitos estudantes, mas estão alguns, e portanto é para esses que a mensagem se dirige na essência, e o que queremos é aproveitar o trabalho que os estudantes já fazem. Como todos têm de ler durante a elaboração do trabalho das cadeiras, das teses de mestrado e das teses de doutoramento, há algumas obras, e aqui a ideia das obras são livros, mas podem ser livros compostos por, como há muitos hoje, a ideia de uma collection composta por uma série de capítulos autónomos, isso também é um livro, como todos têm de ler. A ideia neste caso é aproveitar essa leitura e o registro, digamos, crítico da leitura, sob a forma de recensão, portanto aí é que tem de lhe dar um caráter um bocadinho mais formal, mas no fundo as teses também são elas próprias formais, mas é aproveitar o trabalho que já têm de fazer no âmbito de cadeiras, no âmbito de teses, para fazerem um pequeno texto, que nós dizemos que tenha no máximo 5 páginas, não pode ser mais pequeno do que isso, mas é um máximo de 5 páginas. Depois há umas normas que estão publicadas no site e que nós vamos republicar outra vez, e que o proponham a concurso. Portanto, são 10.000 caracteres, e 5 páginas, mas a gente somos mais rigorosos, 10.000 caracteres, e que o proponham a concurso, sendo que aqui a regra que nós temos é que a obra esteja disponível no acervo da biblioteca, seja o acervo físico, seja o acervo digital. Portanto, muita gente já só lê em digital, sobretudo a geração mais nova, lê muito só digital, e portanto pode ser uma obra digital, que nós aqui vamos alargar provavelmente o período, que tenha sido uma obra relativamente recente, e portanto o que dizemos é os últimos 10 anos, publicada ou republicada nesses últimos 10 anos. Pode ser uma republicação, porque se foi republicada é porque ela mantém interesse e se parte do princípio que aquilo que foi dito continua a fazer sentido para as leituras atuais. Portanto, se fizerem um trabalho que tenha uma componente de leitura de um livro que esteja disponível na biblioteca, em versão digital ou física, relativamente ao qual acham que há um conjunto de ideias interessantes, que tenham fixado e que estejam a usar para um trabalho ou para a tese, transformem isso numa pequena recensão com um máximo de 10.000 caracteres e submetam-na então a este concurso Obras que Contam. Nós vamos abrir isto na primeira semana de dezembro ou na segunda, portanto entre 2 e 9 de dezembro. Vamos deixá-lo aberto até abril, portanto tem muito tempo, é todo o ano letivo para trabalhar. Vamos deixar a forma de envio, que será uma forma de envio digital, com o e-mail do concurso, etc. Portanto é fácil de enviar. E temos uma sessão em conjunto com a Finisterra e também com provavelmente mais algum evento do IGOT ou da biblioteca, onde divulgamos quem teve, digamos, a recensão premiada, digamos assim, mas normalmente a visão é muito ampla e, portanto, no ano passado, por exemplo, eu creio que se candidataram 5 recensões e nós tivemos uma que de facto foi a que teve, digamos, o prémio, mas houve mais 2 que tiveram como é que se diz? Uma menção honrosa, não é? Uma menção honrosa. E se há um prémio, digamos, material, não é? Oferecemos livros, etc., há uma outra componente que é talvez a mais interessante para quem está no início de carreira, que é a divulgação na Finisterra. Como o Marcelo disse, nós já publicamos 2 destas recensões online e vamos publicá-las fisicamente. Esta a mensagem, entretanto o pessoal deslocou-se mais ainda para ali, mas fica a mensagem, e o que apelamos é às pessoas que, sobretudo aos jovens, que façam a recensão, o que significa ler, significa refletir, significa escrever, que é uma coisa que têm de fazer, e significa depois reconhecimento através da publicação na Finisterra, que é claramente uma boa revista. Portanto, façam isso, fica aqui o apelo. Suponho que o Marcelo encerrará a sessão, mas posso encerrar eu. Portanto, acabou, pode ser embora, acabou hoje. Concorram.
Obrigado pela vossa presença e até para o ano. Espero que estejam presentes novamente para o ano. Obrigado pela vossa presença.